it's a class of maths 281. 281. Maths 211. That is set theory and abstract algebra. So we've talked about everything, we introduced ourselves to sets. And now we are going to be looking at Cartesian products of sets. What do we mean by Cartesian products of sets? In this stance, we are talking about how we multiply a particular set with another set. After multiplying a set with another one, what do we have? How do we create a bigger set from the product of two sets? This product now, it's a bit different from the normal product. So we call it the Cartesian product of sets. So look at this. This is a set A. Set A is equal to A, B, C, D. And this is another set B, which is equal to E, F, G. So set A cross B now, your order is very, very important in this case. Order is very, very important. Set A cross B now is A cross B, written this way. That is the product of A and B, the Cartesian product of set A and set B. I'm multiplying set A by set B. I'm going to create a set that is having some other set in it. That means I will first multiply all elements of set B by the first element of A. Multiply all elements of set B by the second element of A. Multiply all elements of set B by the third element of A. And multiply all elements of set B by the fourth element of A. So we go with the first element, that is A. A times E. This is what we mean by the product we are talking about now. We're not going to write AE. Rather, we create a set and we write A, comma E. That's the first thing. Then A and F, that is A, comma F. The next thing, A and G, A, comma G. We've used the first element of set A. Now let us use the second element, that is B. B and E, that is B, comma E. B and F, that is B, comma F. B and G, that is B, comma G. Still continue. Use the third element. C and E becomes C, comma E. The next one, C and F becomes C, comma F. The next one, C and G becomes C, comma G. The next one is now D and E becomes D, comma E. D and F becomes D, comma F. And D on G becomes D, comma G. Now, we've gotten the Cartesian product of A and B. We've gotten the Cartesian product of A and B. This is somewhat different from having B cross A. This is A times B. This is different from B times A. If it were B times A, now let's do B times A here. B times A is going to be using the element of B, each element of B, to multiply all the elements of A. That's going to be E by A. And that gives E, comma A. The next one will be E by B. That is E, comma B. The next one will be E by C. That is E, comma C. The next one will be E by D. That is E, comma D. The next one will be F by A. That is F, comma A. The next one, F by B. That is F, comma B. The next one, F by C. That is F, comma C. The next one, F by D. That is F, comma D. Then we resort to G. G by A. That is G, comma A. G by B. That is G, comma B. G by C. That is G, comma C. And G by D, which is G, comma D. This is the Cartesian product of B and A. That is B multiplied by A. So now from this we can see very well that A times B is not equal to B times A. This is very obvious from the information we are able to. Numbers this time. Using numbers also doesn't mean we'll multiply 4 by 6 and we're having 24. We rather write 4,6. So let's use numbers this time. Or 6, and set Q is equal to 2, 5. Now, what is the Cartesian product of P and Q? So that means the element of Q by each element of P, right? So 3 times 2, that is, we write 3, 2. You are not writing 3 times 2, 6. No. Write 3, 2. The next one, 3, 5, right? It's just by rearranging. It's not like you're multiplying per se. Then the next one will be 4, 2, and 4, 5. The next one will be 6, 2, and 6, 5. That's the case. What if you were asked to do Q times P? Q times P is going to be use 2 first, then use 5 next. 2, 3, 2, 4, 2, 6, then 5. 5, 3, 5 to 4. 5, 4, and 5 to 6. 5, 6. Now we've written P times Q, or we've written Q times P. We can see very well that P times Q is not equal to Q times P. This is it. We can simply call this a set of sets. So that is that about the product of sets, the Cartesian product of sets. Now let us look at some other things. This time I want us to be looking at the relations. Let us look at relations. Relations. And now you have to be attentive. When we mention relations, we know what relationship is, right? When an element is related to another element, that means there's some kind of connection between them. If dash and dash, or if A and B are having a parental relationship, that means A is the father of B, or B is the father of A, or perhaps A is the mother of B, or B is the mother of A. That is by what? A parental relationship. The relationship must be defined. A relation B, now is my example, where my relation must be defined. My relation is a father of, what does my R mean here? That means A is a father of B. A is a father of B. That is what I mean here. Is a father of, if my relation is equal to is a father of. That because I said my relation must be defined. That means what I mean here is A is a father of B. And per se, I can't say that B is also a father of A. It is impossible. The son can never be a father. So A is a father of B is not equal to B is a father of A. A is related to B. It's not equal to B is related to A if the relation is a father. So now, if they are both related now, if they are both related, then I'll write it this way. A and B are subset, or are elements rather. They are elements of the relation. So A comma B are elements of the relation. And what is that relation? R means is a father of. So this is very different from, I mean, what I expressed here. This is another way to express it. A is a father of B. It is different from B comma A now. If I wrote B comma A is an element of that relation R, what I'm saying is B is a father of A. And that is not possible because I can't have A to be the father of B at the same time be having B to be the father of what? Of A. That is what I mean by relation. So let's have a quick example here before we mention the kinds of relation we have. If 3 is related to 9, we know the relation, or I don't know, it is given that the relation is a factor. Very well. 3 is a factor of 9. This can be expressed this way, or 3, 9 are elements of the relation. What is that relation? Is a factor. This is very, very different from 9 relation 3, because 9 is not a factor of 3. It is very different from 9, 3 is an element of the relationship. It is very, very different. Why? Because 3 is the one that precedes, and it is the factor we're talking about. The order is very, very important. 3, 9 is not the same as 9. When the element of the relation, it is a factor. That is the relation. It's a factor. Now we have 3 kinds of relation. We have the reflexive relation, which is what I'm going to talk about first. What do I mean by reflexive? That is simply, when something reflects. When something reflects, that is like this. A is a relation of A. That is, A is related to A. Provided that just this way, A is related to A. And provided that A is an element of a particular set we're talking about. A is an element of a particular set we're talking about. What does this mean? 3 is related to 3, right? If I said this is exactly the same as this is exactly the same as this. Even if I said the relation is, they are equal, the relation is equal to, if I said the relation is equal to, 3 is equal to 3, and 3 is equal to 3, irrespective of the one I bring forward, if I wrote this 3 at the front, or I write this 3 at the back, they are still the same thing. This kind of thing is as if they reflect each other. When you are before mirror, you see yourself exactly in the mirror. That is why the name comes from reflexive, just from reflection. So they are the same. This is what we call so a relation can be said to be reflexive if it occurs this way. What do I mean by symmetric relation? A symmetric relation is just a type of relation that is like I have A is related to B, and it exactly means B is related to A. A is related to B means B is related to A, where A and B are elements of a particular big set. So now let's think of something here. Let me think of something. Let's say 3 plus 2 is related to 4 plus 1. Yes. Do you know 3 plus 2 is related to 4 plus 1? That means 5. The relation I'm talking about now is equal to 5. This is 5, right? And this is also 5. That means I can also write it as 4 plus 1 is related to 3 plus 2. I can write 3 plus 2. Here is my 3 plus 2. Is related to B, which is 4 plus 1. At the same time, I can write 4 plus 1 is related to 3 plus 2, where my relation is equal to. If something like this happens, then we say that it is symmetric. They are just about how. It's about how. That's what we mean by symmetric. They simply mean the same thing. And after that, we have a transitive relation. We have transitive relation. So what do we mean by transitive? What do we mean by transitive relation? Transitive relation is a relation that's just like this. A is related to B, and B is related to C, where A, B, C are all elements of a particular big subset. A is related to B, B is related to C. Let's say that the relation is greater than. If something like this happens, A is related to B and B is related to C, then we have a conclusion that A is related to C with that same relation, where they are all elements of the big set S. So A is related to B. That is, A is greater than B is my example, and B is related to C. B is greater than C. Is it possible for us to say that A is greater than C? I think it is very, very possible. A is greater than B, right? And we know that B is greater than C. Definitely A is greater than C. If something like this occurs, then if something like this is possible, then we say this is a transitive relation. This is a transitive relation. It happens that A is related to B, B is related to C, and it gives an implication that A is related to C, such that A, B, C are elements of the set. If we use greater than, A is greater than B, and B is greater than C, very obvious that what? A is greater than C. Because if A is 3 and B is 2 and C is 1, because 2 is greater than 1, so A is definitely greater than that 1. And here it is here. If something like that happens and is satisfied, then it is a transitive relation. Those are the three types of relation we have. Those are the three types of relation we have: transitive, reflexive, and symmetric. Now let us look at functions. We've been working with functions for a while. Been mentioning functions. So mapping at functions. Functions. Just that the functions we'll be working with here is more of set theory functions. Set functions. So, and this is a function A. It consists of some elements x, y, z. This is another one. B consists of some elements P, Q, R. In function, everything here is said to match anything here. Without this, in function, you should note that an element here must match something here. So this is B. The function is f. If it is sine, it will be sine A. So the function is f of A. The function might be anything. F of gives B. So the A will be known as the set of domain. It is the domain. While the B will be known as the co-domain. A is the domain. It is here. A is the domain. F of A, which is the same as B, is known as the co-domain. Now, the element of A can match any element in B. Let's say X matches Q, Y matches P, Z matches R. So F of X equals to Q, F of Y equals to P, F of Z equals to R. What we are saying is Q is an element of set B, P is an element of set B, R is an element of set B. The three of them are known as the range of the function. Range of the function. These are known as the set of domains or the domains inside the set A, and these are known as the where B itself, which is the set, is known as the co-domain. The co-domain. Now, if something like this happens, is this still a function? If something like this happens, x to q x to r and y to p. Is this a function? No. Why? Because in a function, you must not have two images. You must not have two images for one domain. You can have two domains for one image. You can have like x to q and z to q. This is possible. This is possible. But you can't have it otherwise. This is possible. X is given, that is f of x equals to q, which is an element of b, and f of z also equal to q, which is an element of b. So now, this is function. Now let us look at types of functions. I'm going to stop after the second type of function. So I'll be entertaining every question from those that watch the recorded session. So I have the one-to-one function, which is the injective function. Please note these things very well. I have one-to-one function. We have one-to-one function, which is the same as injective function. What do I mean? That means A, B, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. I'm just talking at 3 here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now I have f of 1 to be equal to 1. F of 2 is equal to 4. F of 3 is equal to 9. This is a function, but let's put it aside. Look at this function. You know that only 3 elements are here, and they do not match all the elements here, right? There is a function here. The function is equal to f of x equal to x squared. That is the function I used here. Square of 1 is 1. Square of 2 is 4. Square of 3 is 9. Now look at this function. 1, 2, 3, 4, 7, 8, 9, 10. 1 to 9, 2 to 7, 3 to 8, 4 to 10. Through this function f, set A, set B, the domain, the codomain, the function. So f of 1 is equal to what? 9. F of 2 is equal to 7. F of 3 is equal to 8. F of 4 is equal to 10. This is what we call a what? An injective function, because all elements have domains. They are all one-to-one. One element to one element, one-to-one, one-to-one, one-to-one. So this is what we call one-to-one function or an injective function. That is what we call one-to-one function or an injective function. I explained this, but it's not an example of one-to-one function. This is just to tell you that there is a pattern for a particular function. This is the pattern of this function. Squared of 1 is, that is f of x. The function is square. So square of 1 is 1. Square of 2 is 4. Square of 3 is 9. That is the function f in this case. So I might as well write square of these things to represent the function. That is what we mean by that. So what is the second type now, which I'm going to mention? That is the surjective function or onto function or onto mapping. We call it a surjective or onto function. The surjective or onto function. What do we mean by that? That is simply telling us, or onto mapping, that we are having range that is having more than one domain in the more than one element in the domain. So this is X, Y, Z. This is A, B, C, D. B. Look at this. B and A are going to 1, right? C to C and D to X. This is what we call onto function. This is what we call onto function. So if the image of the element is at least, if the image of the element is at least a function of, at least, it might be up to 1, it might be more than 1, at least a function of the element in this domain. That is, this is an onto function, but this one here now, 1, 2, 3, 4, 1, 2. There is still 4 outside, right? This is not an onto function. Why? Because there is still an element in the codomain that is not matched with anything at all. So it is not a surjective function. That is what we mean by an onto function or a surjective function. Now there is another one that carries the property of a surjective function and also the property of an property of surjective and the first one, that is injective function. So that one is known as the bijection or bijective function. It's said to be bijective. And it carries the both of them, it carries the both of them. And that is something that is one-to-one, at the same time, it is onto. Onto means all elements here must be filled. One-to-one means it goes to one element. So P, Q, R. Look at this. They are one-to-one, 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 and all elements are filled. So it is a bijective function. Now look at a quick example. This is X, Y, Z, P. P is not filled. But the things that goes on here, it is one-to-one, right? One element to one element, not one element to two elements. One element to, not two elements to one element, rather. One element to one element, one element to one element, one element to one element. But there is an element that is not filled. So it makes it not an onto function. But if the thing is like this, all the elements have their own domains. They have elements in the domain set. That makes it a bijective function. And they say, because it is an injective function, at the same time, it is a surjective function. So, that being the case, we are going to end the class here. If you have any question, you can always put it forward. May God help everyone else. Thanks, mates. Can end it. Thank you very much. Thanks, mates.